Today we're gonna get started for today. So I hope everyone had a great spring break and the weather here is a lot warmer. Um, so today we're really honored to have Tim Dettmers as the guest lecturer. So Tim is an expert in machine learning, deep learning, language models, and especially things related to efficiency. He's done really pioneering work on quantization. If you know techniques such as the ones I presented briefly, like QLoRA, as well as the bits and bytes library, he's the creator of those. And so no better person to talk to us today about efficient foundation models via quantization.
Yeah, thank you so much, Sean. And thanks everybody for coming. It's such beautiful weather. So you rather listen to quantization, huh? So, so today I present you sort of a part of my research that I did in past years, talk then also a little bit about how models are used, quantization is used sort of in industry versus personal use. And so my research is value driven. I want to bring AI to the masses. I want to bring AI to the people so that they not only can use AI, but they can actually um, um, work with AI, make AI their own, fine tune it, adapt it to their use cases, and really learn to work with these models beyond inference to join the workforce with AI skills that they can develop. And so for that, the core part is making foundation models accessible. The main sort of problem that particular sort of happened in the last couple of years, models got really, really good, but also really, really large. And so with that, it became very problematic. People could no longer use these models on their personal devices. And you needed to have a large cluster or lots of expensive GPUs to use them. And so this is the main problem that I tackled. Make these models more efficient, more accessible to give people the opportunity to work with these models and make it their own. And so this lecture, I talk about basically how we can use foundation models more efficiently, mostly through sort of quantization for inference. Then how can we fine-tune foundation models more efficiently? There I talk mostly about QLoRA, and then sort of some practical bits of sort of what is the future of quantization and how does quantization make sense for users versus companies? And so it's also sort of important to talk about like if you do this research and you want to make things accessible, it's like who will be impacted in this research. And for using foundation models, it's mostly people like you, students, PhD students, researchers that do not have so many resources, and they just basically want to figure out what these models can do, learn from them, and adapt them. The fine-tuning is most interesting to researchers that don't have the resources, mostly PhD students. A lot of PhD students use QLoRA, yeah, that's useful for them. And then sort of companies with these users, there's certain perspectives. And for you, this might be if you join a company or as AI is progressing and you want to deploy AI in the future in the company that you work with, the knowledge that you gain here might be useful for that. Let's talk first about the accessibility challenges of these sort of user groups. And what I will do is I give you sort of a brief intro of the problem, the solution that I developed, and then we do a deep dive. Before the deep dive is a little bit of background section. And at the end of the lecture, there will be an interactive sort of session where I show you different, in a simulator, different ways of doing inference and what that means for the user, what that means for the bottom line of the company. And we will learn from that. And so let's dive in. If we look at the accessibility challenges of using foundation models, that means inference, then I hope Zoom is still working. And then the main challenge there is the foundation models got so large, it's just really difficult to use them. People were no longer able to access them. And so we need to compress them. But that has sort of another challenge that comes with it. And you want to maintain the prediction quality. And also you want to maintain the speed. It's not very useful if you can run the biggest, best model on your laptop, but it's super, super, super slow. So we need a certain speed to make it useful. And so the main contribution that I made here was to take 16-bit foundation models with this usual precision that you run foundation models in and compress them to 8-bit or 4-bit. And this was a previously best quantization method before I started my work. And we see on the x-axis the size of the foundation model, on the y-axis performance across multiple benchmarks. And what you see is performance increases, like usually if you scale foundation model, but then suddenly it drops down and actually drops down to random performance for very large models. And this was a challenging problem. People didn't know what was happening here. Why is it happening and how can we prevent it? And so I developed a solution which just scales normally, just like 16-bit, but it actually uses mostly 99% of all computation is done in 8-bit. And I could develop this method by detecting emergent outliers. Once you scale language models to a certain size, they change their computation patterns. And then you need to analyze them to really understand what is going on. How can I compress this computation to 8-bit while still preserving the important information in 16-bit? We will get into the details of that. If we look at the next group that wants to fine-tune foundation models, the main challenge is also quite similar memory. For that, I want to give you a little story. And what we have here is foundation models for biology, protein models. And I talked with a cancer researcher, and she was working with ESM1, which is not as good as AlphaFold, but it's open source. So she can just take it, fine-tune it for cancer proteins, and then she gets basically the structure of cancer proteins. She can predict the new structure of cancer proteins. And she got really, really excited when ESM2 was released, which was in many ways as good as AlphaFold or slightly better. But she downloaded the model, she downloaded the code, and then she realized she couldn't fine-tune it. It was just too big. She didn't have enough GPU resources to do it. And so that is basically the main problem that a lot of people face. The models got really good, but also really big. And if you look at the cost of the system required to fine-tune the largest model at a certain point in time, it costs about $7,000 in 2021. And in February 2023, it cost already $700,000 to buy a system with which you could fine-tune the largest model. And so what I developed was QLoRA. This compresses the memory requirements from like 3 large servers just to a single GPU, a consumer GPU. And this is 4-bit fine-tuning where certain elements are still kept in 16-bit that preserves quality, but you have much more sort of less memory that you need to, so sort of the entire model is compressed to 4-bit and it reduces memory uses. And then the last part, here we will see more when I go through the simulation at the end. But what we will see is companies really care about making inference cost efficient. They want to spend the least money possible to serve tokens to you. And that has a very different structure from users. Users usually want the most tokens per second. They just want to get information fast. And they want to run on a local device, so memory compressed. But as we will see, you cannot have both. And if you're a company, you kind of need to satisfy the users with a certain speed, but you mostly want to optimize for how cost efficient it is. And this is very important. If you hit certain numbers in cost efficiency, there might be billions in revenue for these large companies. So current estimates are that, for example, OpenAI, most of the models that they serve, they have margins of 80% on that. So for every dollar that they spend, they get, well, I mean, what is it, like $5 back? So that's pretty good. And most of it is because they're so cost efficient with inference. Okay, that was sort of a short summary. I also want to talk a little bit about how I work. And so this gives you an idea of how I approach these problems and how certain thinking about these problems might be sort of good to tackle efficiency and accessibility issues. So for me, it always starts with sort of first understanding the models. And here the important part is not to understand this one model, but understand what are general patterns of computation across all models. We don't want to quantize this one model and compress this. We want to do it for all models and do that effectively. And so that's the first part to get an understanding of how these models work and process information. The second step is actually implementing the algorithm. How do we quantize with sort of maintaining the quality, but also getting the speed of generational fine-tuning, maintaining that. But then the third step kicks in, and that is we have particular people that we want to serve. And these people usually don't have big GPU clusters. They might have desktop under their desk with a GPU in it. And so how can we serve those people? And we need to redesign our algorithms to basically serve those people best. And that feeds into the research. And then the last part, for me, it's not enough to have like a paper on archive. I want to bring these things to people. And so there we have to think about how do we package this, how do we open sources and make it actually so that everybody can access this entire method easily. And for that, I created the Bits and Bytes library, implements my research algorithms. The numbers now outdated, I think is growing at more than 2 million installations each month and is widely used across industry. And it's also widely used across all kinds of different sciences. Like people realized these big models, they're good for a lot of different cases outside of computer science. And so they're now used in sort of many different areas with big success. And yeah, with that, I want to give you sort of a little bit of a background. So I'll give you a little bit of background, then we do a deep dive into these sections with more details. Everything will be pretty high level. There will a couple of things where I go in a little bit more detail, but all of this is sort of designed to help everybody sort of stride along in this sort of lecture. So it will not be go into all the research details. At the end of the lecture, there will be a Q&A. So if you're interested in certain details, keep it in mind. You can ask me later. And with that, let's talk about three things. The first is, where are resources used in neural networks? This is an important question because if we understand this, we know where we can improve accessibility because we just need to reduce the resource use in those cases. And it's actually pretty simple. This looks actually very complicated, but it is very simple because this is the transformer architecture. Everybody uses it as an AI, but if you break it down, it has two modules that use 60% of resources, 35% of resources. If you dig down deeper, these are just matrix multiplication. And so the story is, in AI, 95% of memory and computation comes from matrix multiplication. So if you look at just this problem alone, we can solve most problems. But it's a sort of challenging problem, as we will see later. Let's first look at basic details of neural networks. I think this will not be too difficult for you because you're an advanced NLP here, but I just briefly go through these details. So how do neural networks work? We have inputs, x1, a vector, and then we have weights, and these weights basically multiply all the inputs to create an output. And often we create multiple of these weighted sum outputs. And that makes it, we have a full layer that goes from sort of all inputs to all outputs. All these weights are connected, all the outputs are connected to each input. And this is matrix multiplication, x1 times w1, the weight, and that gives us the outputs x2, also a vector. Now, what in neural network usually have many of these layers. And so what we do is we pass the input vector from one layer to the next, and we just go through all the layers. And at the end, we compute a prediction. And this prediction is a probability distribution of the next element usually. So I told you that matrix multiplication uses almost all resources. Now the problem is it's already pretty optimal. Like we cannot improve it much with hardware or with software, but what we can do is we can find approximations that make it a bit more efficient. And not all approximations are created equal. So we have, for example, Some approximations where we have a low rank matrix, we just project down to a small dimension, then project up to a large dimension. The inputs and outputs have the same dimension as the matrix multiplication. And so this reduces computation. We have smaller weights. It's faster, we have less computation. But the problem is this doesn't preserve the quality. This usually leads to a big degradation in performance. This is not a solution that we can use to improve the efficiency of matrix multiplication. Now, another thing that a lot of people think about, and is very appealing, is sparsification. That means that we look at the weight matrix and we see there are a lot of weights that are close to zero. So if we remove them, we don't lose quality. And in theory, we get better speed because of less computation and less memory because we removed weights. But in practice, it's not true. Sparse algorithms are really, really tricky, and they do not run efficiently on modern hardware. And so in most cases, we are slower, way slower. And in most cases, actually, you'll also need more memory to store the sparse matrices because they need special formats. So this is not it's an appealing solution, but in practice, it often doesn't work. And now let's look at quantization. In quantization, instead of doing computation in 16-bit, with 16-bit inputs and weights, we can go down to 8-bit. And now we are twice as fast. We use half the memory. And the only thing that we need to do is maintain the quality to make this solution work. And as I will show you sort of in the next sections is we can do this. It's a bit tricky, but we can maintain the quality. With this, it becomes a very effective solution. Let's talk about quantization, some basics. So in quantization, we take a sort of a high precision number with more bits. We want to compress it to a number with less bits. For example, if you have a 16-bit float, it has a range between minus 65,000 and 65,000. And if we have a 4-bit integer, it just has a range between minus 7 and 7. And so if we have some normally distributed data between minus 3 and 3, and what we do is we take this distribution, just project down to our target distribution, the 4-bit integer. It would look something like this. But here's the problem now. You see each of these blue dots. This represents a bit combination in the 4-bit data type. It has 16 bits, but we don't use most of them. So this is actually closer to a 3-bit quantization. So we lose a lot of information. How can we do better? We first rescale the 16-bit to use the exact same range as the target data type, in this case, the 4-bit integer between minus 7 and 7. And so if we project down now to the closest element, we use the entire data type. And this leverages all bits, and we get more precision. And this is much more effective. So this is basically universally used. There's no reason not to use it. But there's a problem. If we have outliers, if we have very large values, then we cannot rescale. So here I inserted very large outliers at the end of the distribution. And if we now basically rescale and project down, we have still the same problem as before. We use approximately 3 bits, even though we have a 4-bit data type. And so this is a challenge. And this is generally a challenge in quantization. There are outliers in neural networks. But unlike in other engineering disciplines, where people take the outliers and they just throw it away, we can't do this in deep learning. The problem is these outliers usually represent really important values. We need to keep them. Often we need to actually keep them in higher precision. So this becomes challenging. We cannot discard the outliers, but we cannot rescale the distribution effectively. And that is a very common problem. So just to show you what that looks like. So I showed you we have normally distributed data. If we rescale it, we have something like this, where an integer quantization is actually very similar to histogram binning, where you slice your distribution in 16 slices, and each of these slices is a histogram bin, and then we just bin the data into each bin. And this is equivalent to an integer quantization with 16 different bins. Now, with an outlier, it looks like this. that you often see in histograms. You have some bad data and have an outlier at -10. Suddenly, you don't use so many bins anymore for your entire distribution. And that means you lose information in the quantization. Just a visualization that will be helpful later. Okay, with that was sort of the background. Happy to take a question or two now regarding a background, and otherwise we dive now a little bit deeper into the sort of matter. And any questions at this point? Go ahead.
Might seem a silly question, but like we are scaling down 16-bit to 4-bit, so essentially like 65,000 versus 8, like that's very small.
That's right.
We are losing that much, like 64,000 of number information. So how are we compensating for that?
Yeah, so the interesting thing is neural networks are very robust to noise, and some part is how they represent information. So neural networks have multiple neurons, and concepts are usually encoded by activating multiple neurons. And so to recover information of a neural network, what you need to do is you need to distinguish one pattern of activations versus another. And so usually concepts are overlapping. So if you activate a cat and a dog, they're both animals. And so you might have like, I don't know, 8 neurons. And for cat and dog, they overlap a little bit. Now, if you quantize, you wash these things out. And sort of the difference is you might like by accident activate another neuron or turn one neuron off. But it doesn't matter unless, if you can still distinguish these two patterns, the cat and the dog, because the overlap's not too much, it works. But now if the overlap becomes almost identical, you can no longer distinguish, do I have a cat, do I have a dog? That's where the errors occur. So the question is like, how much information do we need in this entire representation of neurons to make this distinction? And there are interesting scaling properties that I'll talk about later that basically say there are limits. These are empirical. They're probably information theory related. And we can no longer go further than that because of sort of these representations. Go ahead.
Yeah, how did you find out that outliers are really important for deep learning?
I'll come to that sort of a little bit later. Any more questions? Otherwise, I move on now. Okay. Basically, we now directly talk about outliers. And so I showed you this quantization method before. That was the previously best one. It fails at scale. And why fails it at scale? I could immediately see that the problem was outliers. But now we have this challenge that if the outliers are sparsely distributed, we cannot extract an algorithm that is efficient because we cannot extract the outliers in a sparse pattern because it's too inefficient to compute, too inefficient to store. So what we need to do is we need to see, is there a structure in these outliers to really develop an algorithm that exploits the structure to have something that's memory efficient and speed efficient while still sort of separating the outliers. If we can separate the outliers, we can normalize the distribution, use the full bits that we have, and just treat the outliers separately. And so that's what I tried to do. But the challenge was, can we figure out a structure in these outliers? And in the beginning, it was very hopeless. And I want to guide you through sort of this process, what it looks like. And it's sort of quite informative because we will see there's a certain threshold where suddenly things change. And so what I have here is a representation of a neural network with a lot of layers. And now what I have here is a red dot, and this red dot represents an outlier. And so what I do is I have this neural network, it's already pre-trained, I pass a Wikipedia article through it, and then I look at where are the outliers. And so I notice some patterns, and this is a small neural network, 350 million parameters. Of course, it has much more layers, but the patterns that I show here in outliers are pretty realistic. That's basically what I saw in my data. That's what I had to work with. And so if you're at a small scale, you have some outliers here and outliers there. There's absolutely no pattern, so nothing you can exploit. And so that was sort of a demoralizing result. It looked like it wouldn't work. But then I went to 1.3 billion parameters, a little bit larger neural network. And so if I looked at different Wikipedia articles, I could see like, hey, there's a little pattern there. Maybe there is something. And so then I worked with 2.7 billion parameters. This was already very difficult at the time. The software didn't exist to do this sufficiently. And so when I passed Wikipedia articles to that neural network, I saw even more outliers. And so then I rewrote my entire code base to try and make it efficient to run larger neural networks. And the first 6.7 billion parameter model that I ran had this. All the outliers are in the same position at all layers. And then I used a different Wikipedia article, still the same. So for all data, for all layers in the entire neural network at the same position, they're outliers. Highly, highly structured. And so at first I thought, this must be a bug. So let's grab a different neural network. And so I grabbed a different neural network. It had still outliers. It was trained with different software. It was trained on different data, completely different, but it had outliers just in a different position. And it also didn't change with inputs. Then I looked at larger neural networks, same pattern, just a different dimension. And so then I said, okay, I think I have a pattern here. Let's plot this. And so this graph took like ages to create. And on the x-axis, we have language modeling performance and complexity. And on the y-axis, we have the percentage of layers with outliers. And so this is a plot. We get a smooth exponential. As language modeling performance improves, we hit a point where we hit 100% outliers. And once we hit that point, every neural network has outliers all the time in the same position and in a certain position that is sort of random, but once it has this position, it never unlearns it. It will always maintain these outliers. So with that, we now know the process of these outliers. It's related to language model performance. And if we draw a line at the perplexity where this occurs, now we look at the magnitude of outliers, then we see that at this point, the outlier magnitude goes crazy. It will grow really, really large. And what I showed you before was if you have quantization, you want to renormalize, the most severe outliers are at the very end of the distribution, because then we can't rescale. And this is exactly this problem. So these are the outliers that destroy the quantization, and these outliers occur in every neural network at a certain scale, at a certain performance. And so now we understand this, and now we can develop an algorithm. The algorithm is very simple. What we do is we look at the dimension where the outlier is. It's different for every neural network, but we just need one input to determine this dimension. Once we have this dimension, we extract that dimension, do a matrix multiplication in 16-bit. That's 0.1% of all values. For all neural networks that are tested, about 0.1%. And then we take the rest, 99.9%, we do an 8-bit matrix multiplication. And then we have these two matrix multiplications, one very large, one very small, and we add them together. And with that, we can recover the full 16-bit matrix multiplication. But now 99.9% of computation is done in 8-bit. And with that, we get these results. And this graph doesn't have the 16-bit line, but it's basically identical to the blue line. There's absolutely no difference. And so that means that we can run neural networks in very low precision if we keep the outliers separate and don't quantize them. And the rest we can quantize very aggressively to 8-bit. And that works really well. And so with that, we could use models in lower precision, large models in lower precision. And so that led me to sort of another question, like, can we do it in 4-bit? But then I asked a more interesting question, and that is a little bit more complicated. How can we maximize the performance density per bit? Let me tell you what I mean by that. If you have two neural networks, one with 10 billion parameters and one with 20 billion parameters, and we quantize one in 8-bit, the other in 4-bit, then these neural networks have equal amount of bits, 80 billion bits. But one of these will have better performance. And so with that, better performance per bit. If you have a memory limited device and you want to get the best performance possible, then the right question to ask is, how do you get the most performance per bit? And that not necessarily how far can you compress it? Because if you compress too far, you lose quality. And so you want to have the best trade-off. How do I get the best quality with the bits that I can store? And so this is the question. And so I analyzed this. And this were lots and lots of experiments, thousands of experiments. On the x-axis, we have the model size, the total bits in the model. And if we quantize it, of course, the bits shrink. We get less bits. On the y-axis, we have performance across several tasks. And so what we see is this is the curve for 16-bit. And the top left is the highest performance density. Now, this is the 8-bit curve. We already know that 8-bit is as good as 16-bit if you do it right, but it's half the size, so double the density. Now, this is a 4-bit curve, and we get a little bit loss in performance, but the memory footprint is half of 8-bit, and so it improves still. And now if we go through 3-bit, we get instabilities. The quality degrades significantly, and this is no longer competitive. And so this means the highest performance density occurs at 4-bit. And I tested this on lots and lots of models, and I found this is always true. We always get the best performance around 4-bit per parameter. And so I looked at different qualities that sort of matter. And I told you before that this is sort of a quantization. You can see there's a histogram. This is an outlier. And now there's a method that works very simple. And what it does, and this is basically the second most important quantization parameter. One is how many bits you use. The other is called block size. And so what that does is you look at the matrix, and it has basically in a matrix multiplication, you multiply a row vector by a column vector. And what you can do is you can take this row and column vector and chunk it in smaller and smaller sizes and normalize each of these chunks, each of these blocks separately. That means that if you have a vector of 1,000 elements, the outliers in the first 100, if you now chunk it into 10 segments, 10 blocks with 100 elements each, the outlier will just be in the first block, but not in the others. And then you get something like this, that the outlier affects the first segment, the first block, but all the other blocks use all the information in the data type because they don't contain outliers. And this is actually a very effective way to improve the quality of your quantization, because with that we can isolate outliers. With the algorithm before, we could isolate outliers in the matrix multiplication because they are very structured. But if you have outliers that are all around, this is one of the most effective ways of doing that, by creating small blocks of elements that you quantize. And so a question was, how large should this block be? Because if you make this block very small, let's say you make it 16 elements, now you store the normalization constant in 16-bit, that adds 1 bit. So if you apply to a 4-bit quantization, it suddenly turns into a 5-bit quantization. And so at some point, we need to use quite a bit of memory to just store these blocks, store the normalization constant. And so that is what I analyzed. And the curves look very close here, but it's actually a very significant improvement. I tested a lot of things. It's one of the few things that matters. And what we see is if we go to a block size around 64, that becomes very optimal. And right now, most algorithms use a block size of 32. And NVIDIA's hardware actually now also implements this. So the new Blackwell GPUs, they use blockwise quantization, and there you can go to 32-bit. So if you use blockwise quantization software, it slows things down. But now that's implemented in the hardware, there's no drop in speed. You're very fast, very precise. That makes 4-bit much better. And with this, you might ask, okay, we went from 16-bit then to 8-bit and 4-bit, and it seems to be pretty easy. How far can we go? And it turns out we can't go much further. If you look at AI progress, it was very much determined by how fast are our GPUs. but GPU speed was mostly achieved by using lower and lower precision. And it's a big problem if we can't go lower, if we can't go to 4-bit training and 2-bit training. And so this is sort of a similar question. At some point, you degrade your performance and you might do the computation faster, but if they don't have the same quality, you need to do more computations. So you have cheaper computations, but you need to do more of them to achieve the same quality. And at some point, these advantages cancel out. The question is, where's this point? Where do the advantages cancel out? What is the optimal precision for training a neural network? And this is sort of a plot that shows you if you train a model in a certain position and then you deploy it, do inference with it, what is actually the optimal precision. And on the x-axis, we have the token to parameter ratio. So if you look at modern models, it's around 100. And we have here validation loss. So it means lower is better. And so for modern models, it seems that if your ratio is already at around 100, what we have, then if you don't do any quantization, you're better than if you quantize to 6 bits. So it seems we are already at the limit for training. So if you train in 6 bits, it doesn't have any advantages already at this point. You can improve the methods, but you see that at some point you can't squeeze more information out of the bits that you have. We already did quite a bit of that. And so it seems that we're coming to limits now. This is another plot that's a little bit more difficult, but it gives you sort of some data points that are aligned with models that are already known. So these are llama models. And I think these are llama 2, 405 billion, 70 billion, and 8 billion. And in this paper, they estimate the equations of when is which precision needed to train a model efficiently. And so if you have a model, so how to read this plot is, let's take the star, which is a 405 billion llama model. And now I want to train it on, now I look at the x-axis, 10 trillion tokens. Then you can read what precision is sort of the minimum precision to give you the highest efficiency. And so there we see around 8-bit we can do. So 8-bit precision is okay if you have 10 trillion tokens. But now if you go to 100 trillion tokens, then you already need 10-bit precision. So you can no longer do 8-bit training and be efficient. You need more bits. And we see if we train smaller models, we actually need a sort of more bit precision to do that training. So if you train an 8 billion model, if you want to do it in 8-bit, then you need to use less than 1 trillion tokens, which is not much data. And so that means that we will probably not make further advances in terms of quantization for training. We're at the end. And this has like wider implications of where we are going. So if our computation speed is dependent on the precision, and the precision is basically we're done with it, then we might have arrived at an age where computation advances slow down. We will not get much larger models because it's just so expensive to train in higher precision. That's the main takeaway here. So this was the first section. Here, the main takeaway from this section is if you understand the fundamental information processing in these models, like the outliers, for example, that we talked about, or how the quantization affects everything with sort of precision and processing, then you can make the processing much more efficient. With understanding, you can make things efficient and maintain the quality. And with that, we move to the next section. If you have a question or two, I'm happy to take it now. I will take more questions at the end. Okay, then we move to the next section. And this is fine-tuning foundation models. And this is mostly about QLoRA. As I told you before, the main problem was models get so big that you need expensive computers to fine-tune them. And that's not easy for PhD students that often need to do this. And so let's talk about the basics of how to fine-tune a model. It's very simple. So I showed you before how we use neural networks. We pass data through them, pass them through the layers, generate a prediction at the end of it. That often is predicting the next element. Now in fine-tuning, we add a couple of extra steps. We compare our prediction with the ground truth. That creates an error. And then we use a training algorithm for neural networks, backpropagation of errors, to pass this error back through the neural network. This generates weight gradients. And now we can use these weight gradients to update the weights just in the right direction to reduce the error. And with that, we improve the quality of the neural network. And then we can pass the next data through the neural network, repeat the process, get the errors, update the weights, improve the quality until the quality no longer improves. And so I showed you the work that I did with 4-bit quantization of how to get the most information per bit, quality per bit. And I applied all those principles to fine-tuning. And I just thought, like, let's try it. Let's see if it works. And so I took a 16-bit neural network. I compressed it down to 4-bit with best practices. Now I'm trying to fine-tune it. And so how that works is you generate a 4-bit computation with 4-bit error. You generate 4-bit weight gradients. Then you update the weights. But what I saw is quality goes down, doesn't work. And the main reason is when I sort of inspected it carefully was that the gradients were actually very similar to the 16-bit gradients, but updating the 4-bit weights with 4-bit gradients is very noisy, and that leads to poor optimization. The right optimization cannot be found at that position. And so the updating the weights is basically the problem here. And there's one way around it, and we can do this with low-rank adaptation. And so how does that work? In low-rank adaptation, we take the model, but instead of passing gradients through the entire model and updating the weights, we freeze the weights. So we don't update the weights. Instead, we add some new layers on top of it called adapters. And these are just sort of tiny layers. And so we only update those weights. And so how that works is we pass data through the neural network into the adapters and update those weights instead of the model weights. Now we can combine this with 4-bit quantization. And this is what we call QLoRA. So we, again, quantize the model from 16-bit to 4-bit with best practices. But now we add 16-bit adapters on top. And so now if we backpropagate, we still have 4-bit errors, 4-bit gradients, but now they flow into the 16-bit adapters. And we can update these 16-bit adapters with 4-bit gradients. And if we do that, quality improves. It actually works so good that I thought, like, we are very close to having the same performance as 16-bit fine-tuning. How can we get the last mile? And for that, I wanted to develop a new data type, a data type that's information theoretically optimal. And you can cast this sort of in various ways, and also like with optimal transport theory. But I want to give you sort of an geometric intuition here that's a bit simpler to understand. And I showed you that integer quantization is very similar to histogram binning, and where each bin has equal width. You slice the normal distribution in 16 slices because you have 16 bits, and then just take all the values in each bin and quantize the middle value of the bin. Now, if you want to do the information theoretical optimal way, you want to slice the normal distribution also in 16 pieces, but now what you want is each piece has equal area. That means that each piece has equal amount of numbers contained in it. And with that, each bit combination always has the same amount of information contained in them. And that makes the information theoretically optimal. And this is what we call the 4-bit normal float. Because it's information theoretically optimal for normal distributions. And I will not talk about that. We quickly can look at results. What I have here is these are llama models of different sizes, and we look at 16-bit and 4-bit fine-tuning. So 4-bit QLoRA and 16-bit standard fine-tuning. Now, the performance on this benchmark, this is actually MMOU. We see that sometimes 16-bit is better, sometimes 4-bit is better. And on average, these kind of cancel out. They have basically the same performance. And so that we have shown that the 4-bit process, QLoRA, is as good as 16-bit fine-tuning. And this is not so relevant anymore. Very old models, but we created this Guanaco model, which was at that time pretty good. It was the best open source model at that time, and also comparable to ChatGPT on certain sort of language models as a judge benchmarks. But yeah, that was a long time ago. Things move fast. But yeah, the main takeaway in here is so 4-bit fine-tuning with best practice is difficult and it actually doesn't work, but we can make small adjustments, but just passing it the gradients to the 16-bit adapters, and then everything works. And again, here sort of the learning is if we analyze everything deeply, we see like where's the problem, then we can fix it. With that, I come to sort of the last part, and this will look at sort of some simulations. Go ahead.
So I guess you showed that you can keep the adapter at 16-bit and then the gradients are 4-bit and it stays fine. So does that idea also apply to just training from scratch? Like, could you have your parameters in 16-bit and only have your gradients in lower precision? Maybe it saves on memory. Or is it still beneficial to have your gradients in more full precision?
Yeah, so DeepSeek did sort of the first open source successful 8-bit training. And there you have sort of a similar story. You still have main weights that are 32 bits, and then you have computation weights that are lower precision. You need to then to sort of generate the gradients, and therefore sort of a complicated thing where something is 16-bit, something is 32-bit, communications is just like in 16-bit. But the story is very similar. If you update something over time, then precision is very important. And for that, yeah, so you can apply it to training. Doesn't quite work with 4-bit, and maybe on the new NVIDIA GPUs, it might work for 6-bit. But the same principles apply to training. Any other questions at this point? Go ahead.
And then just as like as a user of the 4-bit fine-tuning, are there like sometimes gaps in the performance between the full bit and 4-bit that maybe weren't captured by the initial experiments, like now just been out for a while?
Yeah, I mean, there has been like a lot of debate. I did very careful experiments and I couldn't find any problem for any task. But some people say like, oh, it doesn't work here. And that seems to be often related to hyperparameters. Often people use suboptimal hyperparameters just for LoRa fine-tuning. And so if they use LoRa in 16-bit or LoRa or QLoRa in 4-bit, the performance just goes down, but that's mostly related to hyperparameters. Some people told me about some problems that I couldn't investigate, but they said like, yeah, it just doesn't work. I tried everything. And so hard to verify. So it might be that there are some problems. I myself haven't encountered any. A lot of people use it and for them, it just works. I mean, even like 4-bit GRPO, for example, seems to just work with these models, which is like quite interesting. So yeah, still difficult to say. There are probably some problems, but there's also a lot of things that you can do wrong, and then there will be lots of problems.
Very cool questions.
Yeah, go ahead. No, it's fun.
So I guess the data type is optimal for normal distributions. Do you actually look at the distribution of weights that you get from the neural network, and is the normal distribution a good fit?
So the normal distribution is a very good fit, but it's sort of, there's some distributions that have heavy tails,
Mhm.
The tails of neural networks are very weird, that in the sense that you have like almost a perfectly sort of normal distribution, and then you go a wide sort of space sort of in the distance, and then there's a lot of values.
Mhm.
Or not a lot, but a couple. And so it seems that it's mostly normal distribution plus some outliers. And so the normal distribution in itself is not a super good fit for these outliers, but for almost all values, for almost all weights. So interestingly, even if you sort of initialize them in a uniform way, as you train it, it will become a normal distribution. So yeah, the normal distribution is pretty universal, but also the outliers are pretty universal.
Mhm.
Any more questions? Okay, let's move forward. These slides are a little bit less polished. I have to think about them again. What I actually have here. So if you have efficiency versus users versus companies, it's basically one particular thing that for a user, what you want is you send one query to a GPU, and then you want to get your response back as quickly as possible with as many tokens as possible. But what a company wants to do is wants to maximize how much computation, how much tokens it gets out of a GPU per second. And if you want to optimize that, it turns out a single query will only utilize the GPU a little bit less than 1% of its total computational capacity. So if you use a large GPU like an H100 and you send it just a single query, like chat over a chat interface, then you use less than 1% of the computational capacity. So it's 100 times more expensive to use them that way. So companies want to prevent this. So what they do is they batch a lot of people together in large mini batches to serve all of these sort of at once. And so what we will do when we look at the simulation is look at what are the trade-offs if you have certain batch sizes, if you do this. If we talk about inference, there's sort of two different phases. One is a pre-fill phase, and this is basically your prompt. And a prompt, because it's not generated token by token, that means you can generate you process the entire prompt at once. And this is very efficient. So you can actually so if you send a prompt to a single GPU as a single user, you might get like 5% efficiency or 10% efficiency. So you don't need a very large batch size because you can do all these computations in parallel and keep the GPU busy. The second phase is the decoding, token by token. And this is where you really need a large batch size to make it efficient. What you also need to do is cache the previous tokens. So in the key value cache, what you have is basically for the attention, all the previous values that you computed, you need to store it in GPU memory to be accessible if you want to compute the attention for the next token with respect to all previous tokens. So that step needs a large batch size and is very memory intensive, particularly if you have long sequences, like with reasoning models. And yeah, I already talked about this. So for companies, you want to just maximize how many tokens you generate per dollar, which means how many tokens you can generate per second per user. And the users, they just care about the tokens per second. They don't care about how is your GPU sort of utilized. So let's look at a couple of cases. And this is, I will go through this with the script. And so the first thing that we want to do is batch size 1. We compare the user case. And so I have a script here that's a simulation of inference. And what I have here is a H100 GPU. We just take one GPU and we take like different communication protocols. And you can ignore the communication protocols for once, but now we have a table here, and the table has multiple columns. The first is the batch size. This is how many requests are sent at once to the GPU. The second column is the most important for companies. It's the mean flops utilization. That means how much computational capacity do you utilize from the GPU? So if it's at 1% or 0.01, then you use only 1% of what the GPU could give you. And the next is the tokens per second in aggregate. And then the last is tokens per second per user. So this is the most important for the user. And what we can already see, if you look at the extremes, batch size 1, you use the GPU less than 1%. So you pay more than 100 the price of what it could produce in sort of tokens, but you get 277 tokens per second. Now, if you have a very large batch size, 16,000, you utilize the GPU almost to 100%. So you get most of the tokens that you can get from the GPU. But now you get 4 tokens per second per user. Too slow to be useful for most users. The other thing is you need to cache all the attention key value caches. If you look at the size here, it's 800 gigabytes. And that's probably larger than the model that we're using. And if you run a single GPU with 80 gigabytes, you can't run this. It doesn't work. So the most that we can run reasonably in this case is probably on a single GPU batch size of 512. It gives you 67% efficiency, and it gets you 90 tokens per second. And so here can we see if we make certain trade-offs, we get certain basically points where users benefit or where a company might benefit in terms of efficiency. So we already talked about larger batch sizes yield better tokens per second, are more efficient. Mean flops utilization is very high for large batch sizes. Now let's look at multiple GPUs.
Sorry,
Go ahead.
question with this. So how do you, so this is a this isn't actually running on the GPU, right?
Yeah, this is just a simulation.
Okay. How do you compute the MFU? Doesn't that depend on like a particular library you're using for inference?
Yes. So actually, I think here I have like 70 billion llama model. And so a 70 billion llama model has 70 billion parameters. And for forward pass, you need two flops per parameter. So it will be 140 billion computations. Mm-hmm. Now, if you have a GPU, something like an H100, I think has 110 teraflops maximum. And so with that, you can sort of calculate how fast can you, in theory, that's important. So this is not considering software and everything. Yeah, how fast can you sort of calculate in theory all these computations? And then a llama model also has a certain memory size. And then it's like, how quickly can you move that memory through the GPU? Mm-hmm. And so this is peak performance. Mm-hmm. In most software frameworks that are open source, you get about 10% of this. OpenAI gets probably around 50% of this. So they're a bit more efficient. It's very difficult to get very high percentages, particularly for large models. If you look at DeepSeek, actually, they get very high percentages. Also, I think it's also around 50% or so. So, yeah, this is a theoretical model, but still helpful to understand how these factors are related. Good, let's move to 8 GPUs. And so what we see here is that if we use small batch sizes, we get a lot more tokens per second. In the beginning, we had like 277. Now we get 2,000, so much faster. But the interesting thing now is if you look at the batch size, we see the mean flops utilization. It's now very low. So if you have a very large batch size, companies can't deploy this efficiently. And what's the reason for this? The reason is networking. It turns out for inference, if you have multiple GPUs, you need to communicate between these GPUs. It's very, very expensive for inference. You cannot overlap that easily with sort of other computation. And so this uses a hardware interface PCIe 5.0, this sort of standard GPU slot. But then there is sort of special networking hardware that was developed by NVIDIA. And so if you look at that, we actually get good mean flops utilization. So it turns out if you need multiple GPUs, networking is super, super important. Otherwise, you can't really parallelize a neural network for inference. There's also another one, and you see at some point you have sort of overkill. The mean flops utilization is not much better if you have this sort of very sophisticated hardware. Yeah. Yeah.
So that's communication within a single node.
Exactly. Yes. Communication between sort of multiple nodes, it's usually relatively fast, but it's more comparable to sort of this bandwidth. So it actually gets very tricky. Once you go beyond 8 GPUs, parallelization really matters. And if you look at DeepSeek, they figured it out how to do it. But you really need to think about how do I partition all this computation, how I pull it together, and what information do I need when. It's tricky.
What do you see that takeaway from this chart is there's no point hosting your own inference unless you have, say, 100 concurrent users?
Yeah. So if I think about my current research, it actually mostly based on this fact. So if you have a MacBook, you can run some models, but you only use about 5% of the MacBook's capacity because you usually use it just with a single sample. Now, if we develop methods that can actually leverage where a single user sends multiple requests at once, but then gets one back that's sort of higher quality, it can be through all kinds of different ways. You can think about sort of sampling the best sort of response, but you can also think about something like agents where you have multiple agents doing different stuff. They try different solutions. Then sort of they coordinate what is the best solution, and then they give back your solution. And if you use these approaches, it's actually required to make use of the hardware that you have as a user. And so this is an advantage that actually we can use in open source, but I'm not doing this. Companies can't do this. Companies can't deploy an entire GPU just for you. And so that is an advantage that we can leverage. Good. I have like just one more thing, and then I'm happy to take questions. So we have, this is 16-bit computation. Let's use one GPU. Let's go down to 4-bit. So we have, first of all, let's go back to 16-bit. There's one GPU, 16-bit. We get 277 tokens per second. If we have a large batch size, we get 92 tokens per second. Let's go to 4-bit now. And so what we are seeing is that we get much more tokens per second. For small batch sizes. And in this case, let me check this again. Okay, this doesn't have quite what I wanted to show. I think this wasn't actually captured in the simulation that I wrote. So the thing is, if you have a large batch size, then you need to do computations that basically leverage this large batch size. And it turns out if you have quantizations, you need to do this dequantization step. It's very expensive to do it for a very large batch size. And that means actually quantization is really good for consumers. But if it's not supported by your hardware, it's actually very slow if you have large batch size. So quantization good, but if you want to leverage your hardware, really get a lot of mean flops utilization, quantization is only good if it's supported by the hardware. And that means you can't use 4-bit, you can only use 8-bit. And the new GPUs also support 4-bit, but almost nobody has them because they have problems. So right now, if you want to do inference with a large batch size, 4-bit is actually very slow. It's very memory efficient, but very slow for inference. If you use it as a personal user, 4-bit is fast, but only for that case where you send a single request and get a single request back. And that is sort of, I think, the main takeaways. That is what I have. Thank you so much and happy to take questions now.
I did have another question about the outliers. Do you have any intuition? I know it's sometimes hard to interpret why the model does something.
Yeah.
Any intuition for why it's having these outliers and inconsistent locations?
Yeah. So I actually did a little bit of research about this. It didn't end up sort of publishing it, but a very important quality neural network is to forget information. And so you can sort of think about neural network, it gets some inputs, and let's talk about visual inputs because it's sort of easier to visualize. You see sort of this animal and you say like, oh, this is a cat, this is a dog. And sort of what you do is you have this cat and dog features and you sort of expand them, but then you realize, wait, this is the cat. Then you want to delete the dog features to not confuse yourself. And that's actually a very important part of neural networks. You need to remove information to focus down on the information that's actually more critical to the current information processing as you go from layer to layer. And these outliers are the easiest way to do this. The easiest way to do this is multiply a negative number by a very, very large number and add it to your outputs. And if you hit a nonlinear function, it goes to 0. And this is exactly what is happening. So these outliers are consumed in these nonlinear functions. And then there they remove information and then they're recreated in the same dimension. And why are they in the same dimension? It's because it's easier for optimization. If the neural network can always rely on a big number being in a certain dimension, it knows like, okay, if I need to remove information, I just multiply dimension 533 with -4. Or a large negative number. And so you can always realize there's this one dimension, there will be this large number, it always needs to multiply with a certain value. And the part is also, if you learn these outliers, they're either positive or negative. But once they have a certain sign, they never change. And for the same reason, because you want to have this dimension that's reliable, that you can rely on to remove information.
Very cool. Thanks.
You spoke about scaling levels for precision.
Yes.
And how they kind of contribute to this big gains in compute.
Yes.
And so there's the scaling laws for compute that have been working for a long time. But I'm just trying to understand exactly what you're saying when you say that precision, if the scaling laws of precision have helped people get these larger and larger models. Do you think that, like, since these are kind of running out, there's not much more scaling for precision that you can do, that the amount or size of models has to just not grow that much, and you see other bottlenecks for the scaling of models?
Yeah, so a big part of progress in AI was you could train larger models because the cost of training them went down. The cost of training them went down because GPUs went faster and faster. Why did they got faster? Mostly because of tensor cores and lower precision. There was a point where people said, like, you train your neural networks in 16-bit, are you crazy? You need like 32 bits. There was even a time where they say like 32 bits, why you use 32 bits? You should use 64 bits for the precision. And now it seems we're going to 8-bit. Inference is already standard in 4 bits. And it's sort of, we do this because this just helped us to use more computation and we save costs. But if this no longer works, this is no longer an area of improvement that we can rely on. And it seems that's happening. So we had this trend where everything got more expensive, but GPUs also got faster. Now GPUs will no longer get faster and everything will get more expensive. And you can see that it will quickly stop because it's just getting too expensive to scale further.
For the open source quantized models, do you like worry about the quality? Because now that I've learned about the outliers, I worry I'm downloading something where the outliers are not properly accounted.
Yes. So, I mean, it's quite interesting. And this is currently not captured in the academic literature. What you can do is you quantize a model and really take good care of these outliers. But what you do is you have some calibration data. You look at all this data and look at like, where are my outliers? And I carefully remove them for all my data, and you try to make this data as general as possible. But the problem is, if you run into new data when you, as a user, suddenly you have some different patterns, and the quantization breaks down, and your model does some weird things, and you just like, what's going on now? It worked before, and so this is a problem. And so this is actually the nice thing about something like normal float, because it doesn't rely on data for calibration. It's the same quantization for everything, and so you get more robust sort of behavior if you use it across a wider range of sort of data. And so this is the most tricky, because if you look at benchmarks, a lot of quantized models look good, but then if you use it on your data, suddenly it doesn't work. And it's not transparent. And we don't have benchmarks for this. We don't have a way of measuring this. That's, I think, is the most complicated problem. Yeah.
What if, say, I want to use very large batch size, I want to quantize to like 40 memory, I still want to improve the inference. That's possible, right?
Yeah. There are certain trade-offs that you can make. For example, there's one variant that's interesting that says like, I will still want to be very, very efficient, but I don't care of how many tokens per second per user I get. And so what you can do there is basically you have a jagged approach where you have too many batches. You basically advance one, and while you dequantize, you can sort of advance the next one in terms of computation. And so you have this pattern where you overlap one sort of mini batch where you wait for quantization with computation for the other. And if you do this, then you use the GPU to its full extent, 100%. And it's very easy to fully utilize your GPU. But if you do this, it's also slower. And so you get less tokens per second. Now, if you want to just get a very high speed, that's actually more challenging. And I mean, it even goes down back to sort of physical laws. You need to process information. You need to retrieve from memory. And there's just a certain speed you can do it. And that's based on hardware. So difficult to improve there.
Is it doing this back and forth quantizing and the dequantizing helpful? Just let's just say one by one.
You mean this Zagat pattern?
Yeah.
Yeah. So you can use it if you need to process a large amount of information. Sort of, you don't have much memory, and you don't care about the inference speed. So a good way of doing this is you have a very, very big data set. You just want to run it overnight and get all the inference tokens. And that's something you could do. Currently, they're not good software frameworks for this, so it's a bit cumbersome to do. Technically, that's the most efficient way to use your GPU. Yeah.
So you talked about the performance per bits kind of plateauing at 4 bits.
Yes.
But I'm wondering if you tried also looking at potentially applying the same logic for finding outliers to trying to find features that might be able to be expressed in like 1 or 2 bits, or do you get kind of like diminishing return from it?
So it's sort of there's some things. So you can actually go down a little bit further. So there are different kind of outliers. If you treat them, you can go closer to 3-bit. But then if you try an approach where, I quantize this in 1-bit and this in 4-bit and this in 5-bit, and on average, I want to be better than 4-bit. Very, very difficult to do. It seems you can't really cheat neural networks. I tried very hard on this. It's difficult to beat just 4-bit. You can beat this if you carefully consider other patterns in the weights, other kind of outliers. Any more questions?
And I think we're also at time, so it's